So, today we will continue our discussion on principle of hydraulic machines and system design. Today we will discuss about the degree of reactions, velocity triangles, and we will see in detail that depending upon the magnitude of degree of reaction, how we can construct velocity triangles at the inlet and outlet of the pump. And then we will briefly discuss upon that what is the importance of degree of reaction, why you need to know about the degree of reaction for a pump. And before we go to discuss about this, I will discuss one problem which is very important. Probably I have briefly touched upon that in one of my previous lectures. So, to start with, we will discuss that even if we consider a pump, if it is a radial flow pump or axial flow pump, whatever it is. So, the head developed by the pump, head developed by the pump, which is given by Euler's equations for the pump, is H is equal to U2 C theta 2 minus U1 C theta 1 divided by G. So, this is the Euler equation which predicts the head being developed by a pump, whatever it is a radial flow pump or it may be axial flow pump. Now, if we consider that there is no swirl at the inlet, that we have discussed. If there is no swirl at the inlet, no swirl at the inlet, then head developed by the pump can be written U2 C theta 2 by G. In that case, since C theta 1 equal to 0. So, this is the expression of head being developed by a pump, whether it is axial flow pump, radial flow pump or mixed flow pump. Now, even if there is no swirl at the inlet, I mean, then we can express by U2 C theta 2 by G, but if we have swirl at the inlet, then if we have swirl at the inlet, so if we have swirl, at the inlet, then C theta 1 not equal to 0, whether the swirl is having rotation, I mean whether the fluid entering to the pump will have different rotation or we will have a same rotation to that which is having the impeller. Now, if we have a swirl at the inlet, that is C theta 1 is not equal to 0, in that case head developed by the pump can be written U2 C theta 2 minus U1 C theta 1 by G. Now, if I draw the velocity triangles at the inlet and outlet considering a radial flow pump, then I can draw this is the velocity triangles, this is C2, this is CR2, this is C theta 2, this is W theta 2, C theta 2 and this is U2. This angle is beta 2, this is relative velocity, and similarly we have inlet velocity triangles U1, W1, C1, C theta 1 and W theta 1. Now, C theta 2 I can write this expression in a bit different form, that is U2 into U2 minus W theta 2 minus U1 into U1 minus W theta 1. That is, from the inlet and outlet velocity triangles I can express C theta 2 and C theta 1 in terms of tangential velocity or the blade velocity and the component of absolute relative velocity in the tangential direction. So, if I again further do this simplification, then I may get U2 square minus U1 square divided by G minus I can write U2 W theta 2 minus U1 W theta 1 divided by g. Now, we have discussed that if it is a purely radial flow machine, now I can discuss that. So, if I go to the next slide, so what we have obtained, that the head developed by the pump can be written u2 square minus u1 square divided by 2g minus u2 w theta 2 minus u1 w theta 1 divided by g. So, this is the head being developed by the pump, whether it is radial flow pump or axial flow pump. Now, I am taking a case, say let us say case 1. I have solved one problem in one of my previous lectures. If case 1, that is purely radial flow machines, if I draw the impeller, then like this, and the blade will be like straight. And if I draw the velocity triangles at the inlet and outlet, so this is the blade. So, purely radial flow machines, this is W1. So, this is U1, this is W1, this is C1, and this angle is 90 degree, and this is C1. This angle is alpha 1. So, beta 1 is equal to pi by 2. Similarly, if I draw the velocity triangles at the outlet, again I will get velocity triangles like this. This is U2, this is C2, this is W2, and this angle is pi by 90 degree. This angle is 90 degree. So, this angle is 90 degree. Now, so if I try to write this expression for this case, rather if I try to obtain the head being developed by a purely radial flow machines using Euler equation, then I can obtain H is equal to u2 square minus u1 square divided by 2g, and note that here for this particular case, I mean for the inlet and outlet velocity triangles, from the inlet and outlet velocity triangles, u2 itself is equal to w theta 2 and u1 is equal to w theta 1. Then the remaining part u2 into u2 minus u1 into u1 divided by g. So, that is u2 square minus u1 squared by 2g, by g minus u2 square minus u2 square, that is u2 w theta 2 u2 w theta 2 minus u1 w theta 1 by g, and that would be equal to u2 square w theta 1 is equal to u2 w theta 2 and u2 w theta 1. So, you can see that the u2 w theta 2 and u2 w theta 1, that will be equal to again u2 square, because here w theta 2 is, this one is the this is the c theta 2. So, w theta 2 is equal to 0 here, so here this is the c theta 2, here this is the c theta 1. So, here w theta 2 equal to 0 and w theta 1 is equal to 0. So, this term will be into 0 minus u1 into 0 by 0, that means this will go away. So, this is 0. So, that is head developed by the pump will be simply u2 square minus u1 square by g. So, and if I write this expression in a bit different form, that is if the impeller is rotating at an angular velocity omega, so the omega square into r2 square minus r1 square divided by g, and in that case, so in that case, that is for a purely radial flow machines, head developed only by the Coriolis force. So, in a purely radial flow machines, head develop only by the Coriolis force. That is what I would like to say from this exercise. Even if it is not a purely radial flow machines, suppose now I will take an example of an axial flow machines. If I take, rather if I write the expression again, head developed by the pump is equal to U2 square minus U1 square divided by G minus U2 W theta 2 minus U1 W theta 1 divided by G, right. Now, if it is a purely axial flow machines and no swirl at the inlet, suppose if it is a purely axial flow machines, so if I draw a purely axial flow machines and if it is a purely axial flow machines, so this is point 2, this is point 1. So, if it is a purely axial flow machine, then mine it R1 is equal to R2, then D1 equal to D2, that means U1 equal to U2, because U1 is equal to pi D1 n by 60 and U2 is equal to pi D2 n by 60. If that is the case, then head developed by the pump will be equal to U2 W theta 2 minus U1 W theta 1 divided by G. That is the case for head developed by the pump. Or I can write it minus, so I can write it U1 W theta 1 minus U2 W theta 2 divided by G. So, U1 W theta 1, that is U is equal to R into omega. So, R1 omega W theta 1 minus R2 omega W R2 capital omega W theta 2 R2 omega W theta 2 divided by G. So, this is the expression for head which is being developed by axial flow machines, because for axial flow machines, since radius at the radius of the blade at the inlet and outlet are equal. So, here the head developed by only this component, this one, and again we have been able to show that if the we have shown in one day that if the blades are designed following a logarithmic spiral, then logarithmic spiral, if we follow to design the blade, then perhaps it can be shown that this first term is equal to this term, so it will go away. So, that is the case. So, after having this discussion, now we will simply go to discuss about what is degree of reaction. So, if I go to my next slide, then we will discuss about the degree of reaction. So, degree of reaction, degree of reaction of pump. So, what is degree of reaction of a pump and why it is important, and particularly from a degree of reaction we can design the inlet outlet velocity triangle, we can construct the inlet and outlet velocity triangles, and it may help to design also pump. We know that whenever fluid is flowing through the impeller, I mean then there is a rise in pressure. Of course, as I said you that pump absorbs energy. So, whenever we run pump either using electric motor or diesel engine, we are giving some energy input to the system, that means we are rotating the impeller. So, that mechanical energy rotational, that whenever impeller is rotating, that mechanical energy is converted or transferred to the stored energy of the fluid to increase its pressure or velocity, whatever it is. In a pump, our prime objective or entire purpose is to develop head, that is to develop pressure by at the cost of some energy that we are going to input either through an electric motor or diesel engine. So, if our target is to obtain pressure, that is how much energy we are getting. So, whenever liquid is flowing through the impeller, impeller is rotating and there we are having some input of mechanical energy. So, out of that mechanical energy, how much energy you are extracting, rather how much energy you are getting in terms of pressure head. That is very important. So, whenever it is whenever water is flowing through the impeller, there are two different kind of energy. If we talk about head, pressure head, development of pressure head, there are two different types, one is static head and another is dynamic head. So, degree of reaction which gives an indication about that the fraction of static pressure rise out of the total pressure rise in a pump, that is whenever a liquid or fluid is flowing through the impeller of a pump, then what fraction of static pressure rise out of the total pressure rise is there, and that information is obtained from the degree of reaction. So, we can define degree of reaction like this, that this is defined as the ratio of ideal static pressure rise, ideal static pressure rise to the ideal total pressure rise, right. So, whenever we are defining degree of reaction, which is important, which gives us an information about the fraction of static pressure rise is there out of the total pressure rise, because whenever we are handling, rather whenever a pump handling water, then of course our target is to develop head, rather to increase the pressure head of the water, that is total pressure rise. So, out of this total pressure rise, what fraction is the static pressure rise, that is obtained from this quantity, that is degrees of reaction. So, now this degree of reaction is this. So, now we know that the total pressure rise is equal to static pressure rise plus dynamic pressure rise. So, we can write that total pressure rise is equal to static pressure rise plus dynamic pressure rise. That means, static pressure rise, if I now write this expression of degree of reaction, then I can write this is total pressure rise minus dynamic pressure rise divided by total pressure rise. So, that means, this is essentially 1 minus dynamic pressure rise to the total pressure rise, right. So, this is 1 minus dynamic pressure rise by the total pressure rise. Now, if I draw, let us say a radial flow pump, and suppose we are drawing an impeller of a radial flow pump, and which is rotating at an angular velocity omega in the clockwise direction. So, say the impeller is having a few backward curved vane, and if I draw the velocity triangles at the inlet and outlet, then this is outlet velocity triangles, this is C2, this is U2, this is W2, this angle is beta 2, this angle is alpha 2, this is U2, this is W theta 2, and this is C theta 2. Similarly, I can draw velocity triangles at the inlet, this is C1, this is U1, this is W1, this is beta 1, this is alpha 1, so this is C theta 1, this is W theta 1, and it is rotating at an angular velocity omega in the clockwise direction. So, we all know about the component of velocities, I mean absolute velocity, relative velocity, tangential velocity, and different angles, flow angles and blade angles. So, can you tell me from this expression what could be the dynamic pressure rise and the total pressure rise? So, dynamic pressure rise across the impeller when water is flowing through the impeller, then dynamic pressure rise will be equal to C2 square minus C1 square divided by 2g, and total pressure rise across the impeller I am talking about, total pressure rise should be equal to U2 C theta 2 divided by g, that is equal to h. if we do not have swirl at the inlet. So, but for this case it should be minus u1 c theta 1. If we assume, if we consider no swirl at the inlet, then c theta 1 will be equal to 0, then the total pressure rise will be equal to H is equal to u2 c theta 2 divided by g. Now, if I try to put the values of dynamic pressure rise and total pressure rise in the expression of reaction of pump, then what can I write? So, again I am writing that degree of reaction R of a pump is 1 minus dynamic pressure rise to the total pressure rise, and this can be expressed 1 minus C2 square minus C1 square divided by 2g divided by u2 c theta 2 divided by g. So, after simplification I can write this is equal to 1 minus C2 square minus C1 square divided by twice u2 c theta 2. Again we know that if I go back to the velocity triangle, so even outlet velocity triangles like this is W2, this is beta 2, and so this is W theta 2, this is C theta 2, and this is known as flow velocity CR2. This is CR2 is equal to flow velocity. This is CR2 is equal to flow velocity, and this angle alpha 2 is equal to flow angle. Now, this since the flow rate through the pump is in the impeller is same, so Q will be same, so that indicates CR2 will be equal to CR1, where CR1 is the flow velocity at the inlet. Since Q through the impeller is same, it is a flow through the rotating passage or rotating impeller is as if flow through a convergent divergent part. So, flow rate has to be same. In some place velocity is higher, area is less, area is higher. In some places area is less, velocity is higher. So, this is flow velocity at the inlet. So, CR2 is equal to CR1, and from this velocity triangles what can I write? That C2 square, this is C2. So, I can write C2 square C theta square plus CR2 square is equal to C2 square, that I can write, that is CR2 square plus C theta 2 square is equal to C2 square. Now, CR2 is equal to CR1, and then CR2 is equal to CR1, that is C2 square minus CR2 square is equal to C theta 2 square. Now, CR2 is equal to CR1. So, CR2 square minus CR1 square is equal to C theta 2 square. Since if no swirl at the inlet, then C1 will be equal to CR1. If I draw the velocity triangles like this, that this is, if I draw the velocity triangles like this, this is W1, this is C1, this is U1, this is 90 degree. and this one itself is CR1. So, if no swell at the inlet, from this diagram we can see that C1 is equal to CR1. So, if I put the value of this here, then I can write C2 square minus C1 square is equal to C theta 2 square. That means, if I take this value over here, then I can write 1 minus C theta 2 square divided by twice U2 C theta 2, that is 1 minus C theta 2 by twice U2. So, this is the degree of reaction for a pump. Now, again we can manipulate it that you know that degree of reaction C theta 2 by W2 I can write, because 1 minus C theta 2 is how much? U2 minus W theta 2 divided by twice into U2, that means 1 minus half into 1 minus W theta 2 by U2, W theta 2 by U2, W theta 2 by U2 is equal to how much? W theta 2 by U2, that equal to W theta 2 by U2 CR2 by U2 tan beta 2. Now, from outlet velocity triangle I can write W theta 2 divided by CR2 is equal to quad beta 2, right. So, I can write it that W theta 2 is equal to CR2 quad beta 2 divided by U2, CR2 quad beta 2 by U2. So, degree of reaction of a pump after doing this exercise, I can write this is 1 minus half into 1 minus CR2 quad beta 2 divided by U2. So, this is the expression for the degree of reaction for the pump, that 1 minus half into 1 minus quad beta 2. So, this is the expression of the reaction of a radial flow pump. Now, we can discuss a few different cases. So, let us say if I take different values of R. So, first case I will discuss that when R is equal to 5. So, R again I am writing R is equal to 1 minus half into 1 minus CR2 cot beta 2 divided by U2. So, this is the expression for the reaction of a centrifugal pump. Now, I can consider the different values of R. So, let us say R is equal to 0.5. If R is equal to 0.5, then half equal to 1 minus half plus half into CR2 cot beta 2 divided by U2. So, that means we get half CR2 cot beta 2 by U2 equal to what? That equal to, that is 0, right. So, then from this expression what can I obtain? That is beta 2 is equal to, from this expression half into CR2 cot beta 2 by U2 is equal to 0 if R is equal to 0.5, then from there I can express that it would be what? I mean, from this expression I can tell that if R is equal to 0.5, then it is, or I can write in a bit different form. Let us say I can write, I am writing that half into CR2 by U2 tan beta 2, that equal to 0. So, now this is for which values of it is, I mean this is true, that is beta 2 is equal to. So, from here we can write beta 2 is equal to 90 degree, that is for R is equal to 0.5, beta 2 will be 90 degree, that is it is a purely radial flow machines, purely radial flow machines or radial flow pump. If degree of reaction is half, then this will be purely radial flow pump. Now, I will take another example, suppose case 2. this is for case 1. If I take case 2, let us say r is equal to 0, then so if I r is equal to 0, then if I try to recall the expression of r is equal to 1 minus dynamic pressure rise by the total pressure rise. So, r is equal to 1 minus dynamic pressure rise by the total pressure rise. Now, if r is equal to 0, then dynamic pressure rise will be equal to total pressure rise. This indicates that static pressure rise is 0. Static pressure rise is equal to 0. So, that means for a degree of reaction, when degree of reaction is 0, from the definition itself we can see that the static pressure rise is equal to 0. Now, we will take up another example. If r is equal to, so for r 0.5 beta 90 degree, the purely radial flow machine. Now, I will take another example, r is equal to 1. So, I will take case 3, that r equal to 1. So, r is equal to, again I am writing 1 minus half into 1 minus CR2 by U2 cot beta 2. So, if r is equal to 1, so for r equal to 1, then this degrees of reaction will be how much? Then it will be half into 1 minus CR2 by U2 cot beta 2, that will be equal to how much? So, if r is equal to 1, then for this case half into 1 minus CR2 by U2 cot beta 2, that will be equal to 0. That means CR2 by U2 cot beta 2, that will be equal to 1. So, this expression will be equal to 1. So, CR2 by U2 into cot beta 2, that will be equal to 1 if r is equal to 1. Now, if we draw the velocity triangles at the outlet, if we draw the velocity triangles from the outlet, then what will be the case? So, for r is equal to 1, CR2 by U2 is equal to tan beta 2. That means, for r is equal to 1, I can write CR2 by U2 will be equal to tan beta 2. Right. So, CR2 by U2 tan beta 2, that is the case for r is equal to 1, and what is the consequence of this expression? That means, if I now try to draw the velocity triangles at the outlet, I mean suppose this is the velocity triangles. So, CR2 by U2 is equal to tan beta 2. So, this is U2. So, this is U2 and CR2 is, suppose this is the absolute velocity at the outlet. So, this is CR2 and then CR2 by U2 tan beta 2, that means U2 should be perpendicular. So, this angle is beta 2, right. So, CR2 by U2 is equal to tan beta 2, that is beta 2 is equal to pi by 2, that is beta 2 will be equal to pi by 2. So, this velocity W2 will be perpendicular radial outlet. So, if that is the case, now head developed by the pump will be how much? Then head developed by the pump will be equal to H is equal to U2 C theta 2 minus U1 C theta 1 divided by G. Now, if no swirl at the inlet, if I assume no swirl at the inlet, in particular that is true, or even we can consider swirl, or if we do not consider swirl. So, if we consider no swirl at the inlet, then C theta 1 is equal to 0. So, from this we can write H is equal to U2 C theta 2 by G. Now, for r is equal to 1, we have obtained that this is the velocity triangles that U2 W2 should be radial. So, now it should be equal to u2 c theta 2 will be equal to how much? u2 minus w theta 2 divided by g. So, if I now look at the velocity triangles at the outlet, then what about w theta 2? Then what about w theta 2? CR2 by tan beta 2, because w theta 2 is equal to w theta 2 is CR2 by tan beta 2, because if I draw a velocity triangles, suppose if I draw a velocity triangles like this, outlet velocity triangles. So, this is the case CR2, this is w theta 2 and this is c theta 2, this is angle alpha, this is beta. Now, this is w2 and this is u2. So, what can I write? W theta 2 I can write in terms of CR2, that is CR2 by w theta 2 is equal to tan beta 2, that I can write, because from the inlet triangle I can write that, from here I can write w theta 2 divided by CR2 is equal to again cot beta 2 or CR2 by w theta 2 is equal to tan beta 2, that I can write. That means w theta 2 will be equal to CR2 by tan beta 2, right. So, if w theta is equal to CR2 by tan beta 2, then if I now try to express the, if I try to relate the expression which is obtained for r is equal to 1 and this expression, while, so now for r is equal to 1, CR2 by u2 is equal to tan beta 2. Now, from these velocity triangles I can write CR2 by tan beta 2 is equal to how much? W theta 2. So, that is u2 is equal to w theta 2, that is what we are getting from this. So, if we compare these two expression, then we can obtain u2 is equal to w theta 2, and if I plug in the value, of this quantity over here, then I can write h is equal to u2 square minus, sorry, u2 into u2 minus u2 by g, that equal to 0. That is, for degree of reaction 1, the head developed by the pump will be 0, that is that we have been able to show that if there is no swirl at the inlet, we have seen that CR2 by u2 is tan beta 2, that is it is a purely radial outlet, because CR2 by u2 is equal to tan beta 2, and from the outlet velocity triangles we have been able to show that I mean we will get some velocity component if we use this velocity triangle CR2 by u2 is equal to tan beta 2, then it is radial inlet, and then head developed by the pump will be u2 c theta 2 by g, that is u2 minus w theta 2 by g. So, here w theta 2 itself is equal to how much? W theta 2 0, that is u2 square by g. So, u2 square by, that will be u2 w theta 2 is here is equal to 0. So, u2 square by g, or even if we apply that, if I apply degrees of reaction 1, and if we draw the velocity triangles beta 2 and alpha 2, and from there we have been able to show that for this particular case, if we consider r is equal to 1, then net head developed by the pump will be equal to 0. Okay. So, now I will draw a figure that we have seen that depending upon the magnitude of r, and of course the blade angle, these two are very important to obtain the head developed by the pump. So, now if I draw r versus beta, that is this is blade angle beta and this is r. So, we have seen that for r is equal to 0.5, this beta is equal to 90 degree, right. So, this is 90 degree when r is equal to 0.5. Now, depending upon the magnitude of CR2 by u2 tan beta 2 or cot beta 2, whatever you say, CR2 by u2 is equal to tan beta 2. So, depending upon the magnitude of CR2, flow velocity divided by tangential velocity flow coefficient, it is called flow coefficient at the outlet, we can obtain several values of and degrees of reaction like this. So, if I plot it now, it will be like this. So, this one is equal to CR2 by U2 for 0.4, this one for CR2 by U2 is equal to 0.3 and this one for CR2 by U2 is equal to 0.2. So, depending upon the magnitude of CR2 by U2, that is flow coefficient, flow velocity to the tangential velocity, we can obtain different degrees of reaction for different values of beta. That is what this plot is indicating. So, not only that, depending upon the magnitude of degree of reaction, we can again construct, depending upon the magnitude of degree of reaction, we can again construct, we can design the axial flow pump, and that we will discuss in the next class. And I also will discuss a few problems which are very important, rather based on the lectures whatever we have discussed, rather based on the previous lectures, we will work out a few numerical problems, and probably that problem we will discuss in our subsequent lectures. And so, if I try to now summarize whatever I have discussed today, is that we have seen that for a purely radial flow machines, the head developed by the pump is only because of the Coriolis force. On the other hand, if we have seen that even if it is a purely radial flow machines, and not only pure radial flow machines, if the blades of a central radial flow pump are designed following a logarithmic spiral, I mean sometimes blades are designed following a particular shape. So, if we use logarithmic spiral to design the blades, then it can be shown that R1 omega theta 1 that is equal to R2 omega theta 2. So, in that case the second term will be 0, in that case head developed by the pump will be only because by the U2 square minus U1 square by G. And then we have discussed about the degree of reaction, that is very important, that degree of reaction is very important in the sense that whenever we are using pump, that is essence the objective is to develop a pressure. So, whenever fluid is flowing through the impeller, there is a rise in static pressure as well as dynamic pressure. So, what pressure, that is there is a total pressure, that is static plus dynamics. So, the fraction of static pressure, how much fraction of static pressure is developed out of the total pressure in a pump, that information is obtained from the degrees of reaction, and depending upon the degrees of reaction we can construct velocity triangles, and that what we have discussed today are for different values of r 0.5 and 1. R is equal to 0 is a case when beta t is 90 degree, that is a purely radial flow machine, and for R is equal to R is equal to 0.5, that we have discussed a purely radial flow machines, and R is equal to 0 where we have seen that the static pressure rise is of course is equal to 0, there is no static pressure rise, and from a value of R is equal to 1, rather for a value of R is equal to 1, we have been able to show that the head rise, head developed by the pump is equal to 0, and then we have discussed about the it depends upon the CR2 by U2, that is tan beta 2, and then we have tried to plot a value, plot R versus beta, and we have seen that when when beta is equal to 90 degree, R is equal to 0.5. Now, depending upon the magnitude of CR2 by U2, that is flow coefficient, if we change beta, then what will be a degree of reaction, that is obtained from these plots. Okay, we stop here today, and I will continue in the next class. Thank you.